Hello and welcome to yet another video of Cornerstones of Math. A ball has a shape that can be generated by revolving the graph of y equals x squared about the y-axis. Here, x is from 0 to 1, so it is a finite ball. Initially, the ball is completely filled with water. Next, a solid spherical ball of radius r is placed in the bowl so that it sinks to the maximum possible depth. You know, something like this. Find the volume of water that overflows for three different cases. The first case is when the radius r is 1/3, the second case is when r equals 1, and the third case is when r equals square root of 5. Alright, so this calculate the volume part is not a problem at all, because that's the stuff you learn in your basic calculus course. What we have to take a closer look is the geometric aspect of the problem. Consider a circle that has radius r and the center located on the y-axis. If we move this circle along the negative y direction, it will eventually make contact with the graph of y equals x squared. But what kind of contact do they make? From the figure, it seems that if the radius r is small enough, the circle can move down all the way to the origin, thereby having only one contact with the parabola at y equals 0. But when the radius r gets bigger, it seems that the circle cannot move all the way down to the origin and touches the parabola at 2 points. So we have to mathematically verify some speculations here. Is it possible for the circle and the parabola to meet at only one point when r is small? If it is, then what is the critical radius that beyond that radius, it becomes impossible for the circle and the parabola to meet at only one point? First, assume that, just like the first case, the circle can indeed touch the parabola at the origin. Then the center of the circle becomes 0, r, so that the equation of the circle is x squared plus y minus r squared equals r squared. Now let us find the x-coordinate of the intersection points between this origin passing circle and the parabola y equals x squared. In order to do that, we replace y in the equation of the circle with x squared. Then we have x squared plus x squared minus r squared equals r squared. So x squared plus x to the power of 4 minus 2rx squared plus r squared equals r squared. So x to the power of 4 minus 2r minus 1 x squared equals 0. So x squared times x squared minus 2r minus 1 equals 0. Let us ponder on this result. Notice that if 2r minus 1 is positive, which means that if r is greater than 1/2, then x squared can have two real values, 0 and 2r minus 1. This means that the circle and the parabola can have contact points in addition to x equals 0, here and here, hence not having only one contact, but 3 contacts. Therefore, in order to have only one contact, the radius r must satisfy r is less than or equal to 1/2. Now that we have the exact pictures on how the circle and the parabola meet, let us actually try to solve the problems. First, when r equals 1/3. In this case, the radius clearly satisfies the condition of being less than or equal to 1/2, so the circle and the parabola have only one contact. In other words, the ball can sink all the way down to the very bottom of the bowl. Moreover, since 2r is 2/3, which is less than 1, the ball completely submerges in the water. Therefore, the volume V of the water that overflows is simply the volume of the spherical ball, so 4/3 pi times the radius, 1/3 cubed, which is 4/81 pi. Next, when r equals 1. Here, since r is greater than 1/2, the ball cannot descend all the way down to the very bottom of the bowl. It has to stop somewhere before reaching the bottom, meaning that the circle has to contact the parabola at 2 points. Since the circle does not touch the bottom, the y-coordinate of the center of the circle is not r. Therefore, let 0, b be the center of the circle, and let us find the value of b. The equation of the circle is x squared plus y minus b squared equals radius squared, so 1 squared. We have to find b using the fact that this circle touches parabola at only 2 points. This means that there are only single value for the y-coordinate of the intersection points. In order to use that fact, let us substitute x squared with y from the equation of the parabola in the equation of the circle. Then we have y plus y minus b squared equals 1. And if we expand this, we have y squared minus 2b minus 1y plus b squared minus 1 equals 0. The solution of this quadratic equation represents the y-coordinates of the intersection points between the circle and the parabola. Since there must be only one y-coordinate, this quadratic equation must have only one distinct root or double root. Therefore, its discriminant must be 0, so 2b minus 1 squared minus 4 times b squared minus 1 must be 0, so 4b squared minus 4b plus 1 minus 4b squared plus 4 equals 0, which gives b equals 5 over 4. This means that the center of the sphere is 0, 5 over 4. Notice that since b is greater than 1, the ball only partially submerges in the water, and the volume of the water that overflows is this portion of the sphere. Since this coordinate is 5 over 4, and the radius is 1, this coordinate is 1/4. So now we calculate the volume by revolving the portion of the circle about the y-axis. Since the y-coordinate ranges from 1/4 to 1, volume V equals pi times integral x squared dy from 1/4 to 1. And from the equation of the circle, we have x squared equals 1 minus y minus 5 over 4 squared. So using this, the volume is pi integral 1 minus y minus 5 over 4 squared dy from 1/4 to 1. And if we integrate, we have y minus 1/3 y minus 5 over 4 cubed, which gives the answer 27 over 64 pi. And that was the second case where the ball cannot touch the bottom. Now what would be the third case? Now for the third case where r equals square root of 5. In this case, we intuitively know that the radius becomes so large that the ball will touch the very top part of the bowl. That is, the circle will touch the parabola at y equals 1. To strictly show this, let's use the same approach as in previous problem. That is, we assume the situation that the circle and the parabola are tangent, just like the previous case. And we let 0, b be the center of the circle, just like the previous case. The only difference here is that now the radius is square root of 5 instead of 1. So the equation of the circle is x squared plus y minus b squared equals square root of 5 squared. Substituting x squared with y, we have y plus y minus b squared equals 5. So y squared minus 2b minus 1y plus b squared minus 5 equals 0. When the circle and the parabola meet at only 2 points with the same y-coordinate, the quadratic equation must have only one distinct root, so the discriminant, which is 2b minus 1 squared minus 4b squared minus 5, must be 0. And if you solve this, you will obtain b equals 21 over 4. Now we substitute this value of b in the previous equation to actually find that double root. So 21 over 4 here and 21 over 4 here. This simplifies into y minus 19 over 4 squared equals 0. giving the double root y equals 19 over 4. This means that if we assume the situation where the sphere touches the wall of the bowl, like previous case, then the y-coordinate of the intersection points is 19 over 4, which is the invalid situation in this problem because the bowl has the height of only 1. Therefore, the realistic situation in this case is that the circle passes the very top point of the parabola, which is 1, 1. So now that we've established that, let us find the actual location of the center of the circle. Let 0, c be the center of the circle that touches the parabola at y equals 1. Since the distance between 0, c and 1, 1 is equal to the radius of square root of 5, by the Pythagorean theorem, this length is 1, so 1 squared, and this length is c minus 1, so c minus 1 squared equals square root of 5 squared. So c minus 1 squared equals 4, so c minus 1 equals plus minus 2, so c equals 3 or minus 1. Since c must be greater than 1, c equals 3. This means that this coordinate of the bottom of the sphere is 3 minus radius square root of 5. Therefore, the volume V of the water that overflows is pi times integral x squared dy from 3 minus square root of 5 to 1. And since the equation of the circle is x squared plus y minus 3 squared equals square root of 5 squared, we have x squared equals 5 minus y minus 3 squared. So we have integral 5 minus y minus 3 squared dy, which gives 5y minus 1/3 y minus 3 cubed. And if you calculate this, you will obtain 10 square root of 5 minus 22 divided by 3 times pi. If you're interested in this video, consider this problem. So there's a parabola and there's a point located on the y-axis. And we want to find the minimum distance between this point and the parabola. Now, is this the minimum distance? Or is this the minimum distance? Or does that depend on the position of this point? If you want to find out, please go check out this video, and also don't forget to press that like and subscribe buttons, and I will see you in another video.